Laboratory 2, the steady state heat exchanger. In this lab, we're going to explore a double pipe heat exchanger at equilibrium state. In order to do this, we've set up 5 pipes with circulating water that will be going through from the ground, up through and out of the system. During the course of this adventure, the water is going to be heated by steam in countercurrent, starting with the first pipe, and then subsequently cooled via cooling water via all 4 other pipes, finally draining out at approximately here. The goal of this laboratory will be to find the overall heat transfer coefficient for the entire system. You're going to be doing this both experimentally and theoretically through a combination of different relationships that will involve the Nusselt, Prandtl, and Reynolds numbers. All right, this is the heat exchanger apparatus. As you can see, as was mentioned in the theory portion of this video, we have the heating component pipe, which will draw water from this reservoir up through the pipe, down through each one of the cooling, and then finally out to drain. When we come into this laboratory, we have to make sure that we discuss the appropriate safety considerations. This lab, in the grand scheme of unit operation labs, is fairly benign. We do have high pressure steam that will be doing the heating, however, is mostly contained and well insulated. The main safety consideration for this lab will come from working in and around other unit operation laboratories. To our left, we have the liquid-liquid extraction and distillation. Each would have their own safety considerations. And on the right, we have the evaporation unit and possibly CO2 or the SO2 gas liquid extraction. Each one of these carries their own concerns, and you must always be aware of your surroundings. We also will have students working above us. Therefore, whenever we're working in this laboratory and on this apparatus, it is a requirement that we have steel-toed boots, hard hat, safety glasses, and lab coat. Not only for this lab, but for working in the environment. So, this laboratory will draw, as mentioned, water from this reservoir. This must always be maintained full of water. In order to turn on the cooling water for the entire system, which is the first thing that you should turn on, the switch is located well into the back and will usually be turned on by the TA prior to your arrival. If you can hear the water flowing, and you will see at the end of the steam unit, the cooling will always be draining into the drain. This is how you know the cooling water is on. We can begin to fill this reservoir, opening this valve. It'll fill up to the top and will then begin to drain the overflow into here. You want to balance this by throttling back the T to the point where you can maintain the level of this reservoir at about this height, pretty much at the exit point. If it gains too low, you'll run the pump dry and your experiment will fail. In order to turn on the pump, you pull this. You'll hear the centrifugal pump turn on, begin pumping water through the feed supply gauge. Currently it's shut off. We're going to slowly open the valve, which will allow water coming from this tank to begin moving all the way through the system. We can check and make sure. First, we can see that yes, by reading from the top of this gauge, we are beginning to allow water to flow through the apparatus, and we can check our computer system. All of the temperatures for this laboratory are collected via 6 thermocouples located throughout the instrument. We have steam outflow, steam in, we have the cooling water, the circulating water at each different point, at the beginning of the cooling, middle of the cooling, and exit of the cooling. And we have the circulating water, as shown on this diagram. Each one of these 8 temperatures will be also recorded on the strip chart when you tell the program to start collecting data. It would all be automatically written to a file every second. You can take that data and analyze it after the laboratory. In order to begin the collecting, right now it's showing all the temperatures live. In order to begin collecting, you must make sure that this box with this light is turned on with the switch at the back. And then this controls the turning on and off of the data acquisition program. If I hit start, I'm now writing to file every temperature, every second, and the pressure from the steam. Once I stop, the data will no longer be collected, but you can see via the program what all the temperatures are in real time. So, currently we have regular circulating water going through the entire system. In order to turn on the cooling water has been on since the beginning of the experiment. It's the first thing that we turned on, but in order to run it through each one of these pipes, we have to set the flow rate via this gauge. I'm going to slowly again engage the cooling water. I've currently chosen the flow rate of 2 gallons per minute. Make sure that you take a look at the units and see what it's corrected for. This will have a bearing on your overall energy and mass balance. Now we're running water through the entire apparatus. The cooling water is moving counter current, but we are currently not heating the unit. This is the last step that you should take in order to run the operation. In order to engage the heating steam, you'll come over here and you'll turn on the master steam valve. Only do this with the TA supervision. Once the steam has been engaged, you'll notice the pressure of the steam. Currently in the summer, we have no steam, but you should see approximately 20 to 30 pounds per square inch gauge. If you do not see this number or see much higher, seek out one of the instructors immediately and we'll correct the steam issue. The steam will travel through here where it'll encounter a steam trap, which will allow any condensed steam to be removed from the system so that during the course of the experiment you are working with saturated steam. This will be imperative so that you can go to the steam charts and get an appropriate temperature for and the amount of energy within the steam that will be transferring within to the circulating water. The steam will travel up, interact with the circulating water here. The condensed will again move through a steam trap, come out of the pressurized area, will be collected or condensed and then collected here. Once you begin the collection, this solenoid valve will engage and the condensed steam will begin to fill this reservoir. The amount of steam condensate that you collect over the course of your sample collection period, usually 15 minutes, will be how you determine how much energy is transferred from the steam into the circulating water. Once you have the total energy balance for the system, you'll have the total changes of temperature, you know the properties of water, and you know the driving force is that difference in temperature. You know how much energy is transferred, you'll be able to find the overall heat transfer coefficient experimentally. So, as mentioned, you'll be running this in equilibrium for about 15 minutes. How do you know when you've achieved equilibrium? This is a question that we get every single year, and it'll be different for each different flow regime. If you have more circulating water moving through the system and less heating, it may take less time to reach that equilibrium than if you're applying a significant amount of heating. You must, at minimum, you must calculate the residence time, depending on your feed supply rate, the residence time of the water throughout the entire system. You know you're working with approximately inch-long pipes. You have just over 2-meter sized pipes. You have 5 of them. How long is it going to take for 2 gallons of water to residence throughout the entire system? This is the minimum amount of time that you'd have to wait for equilibrium to become established. And once all the temperatures have stopped changing for a period of time, you can then believe you're in equilibrium and begin collecting the data for your experiment. In order to shut down the experiment at the end of the laboratory, the first thing that must be shut down is the steam. Once again, we're going to shut off the steam valve. And you will see the pressure drop as the steam is consumed within the system. Next, you can shut off the feed supply system. And finally, the circulating pump. Then you will watch the temperatures, and once the temperatures have come down, approaching room temperature, you can finally shut off the cooling water and the feed supply.
We have discussed already some of the hazards associated with using steam and the possibility of getting a burn. There are other hazards that are possible in this lab. One of them comes from the fact that we have electric circuits. The system that we are using, the computer and the pump and these switches, use different voltages. The main voltage that we have here is 110 volts of alternating current, and you have to have the same logical precautions that you have everywhere. For example, do not stick a piece of metal screwdriver down there in the outlet, right? But we have also low voltage cables and connections, and there's water running. So there's another cause of care. Don't try to say, oh, what happens if I put my hand in the water and I touch this, right? Might be silly, but the experiment lasts for a long time. Sometimes you're sitting there waiting for the system to equilibrate, and you might find just interesting to test what happens when I put a piece of metal bar between here and there. Just don't do it. Then also there's other less possible hazards, but they exist. So, for example, don't run around, don't throw things. They pass me the calculator, and then you throw it. Other than it's a bad idea to throw calculators around because they probably break. You might hit someone, or the person might slip, etc. If your pen falls down and you are going up, you might bonk your head against the edge of there, but that's why your hard hat is for. But when you bend like that, the hard hat tends to fall out of your head. You go up, and then you bonk your head again. This might seem simple, silly things, but it happens. There's a ladder over there where you step up, you could hit it. Again, please be aware of your surroundings. There's going to be other groups of people working here, doing the labs or doing experiments for the research, so be mindful of those surroundings always. If there is an emergency, as always, you go out through the emergency exit. If it's an emergency that you think requires pulling the alarm, either because there's a big chemical spill or there's an actual fire, then do so. And don't second guess yourself. It's okay if it was a false alarm. It's better to create a stop system because of a false alarm than don't stop it when it was necessary. Everybody is going to be wearing a badge with the name. So if somebody is doing something that you think is dangerous, call them by their name. They're saying, hey, you're gonna hit the thing. That doesn't help anyone in any way. So, Mary, careful with your head. That's a specific thing. Or Joe, don't touch the valve without gloves. Something specific, the person can stop the action. As you are aware, our system is connected to a computer that provides data recording and data display. In this schematic, we have represented the heat exchanger, and you have the 5 different pipes, 1 for heating, 4 for cooling, and each one of these numbers represents one type K thermocouple. The thermocouples read the temperature locally, then go through a filter, and then the data are read by a program that was written in LabVIEW. These 3 temperatures correspond to the circulating water, these 2 correspond to the steam, and these 2 to the cooling water. So here we have the cooling water coming in, and it goes in the outside of the pipes, and it goes out. Here we have the circulating water coming in from the pump. It goes into the steam heater and then comes out at the top. So we have this middle circulating water thermocouple is located at the end of the first pipe. And that is the exit of the first part of the heat exchanger and the entrance to the cooling part of the heat exchanger. So after this whole trajectory, here is circulating water out. These temperatures are displayed in a diagram here over time, and when you change the flow rates, you will wait until the temperatures are steady. Here you have the pressure also represented in this graph. This pressure is read from a transducer that is located exactly behind the display, the gauge display on the panel, and it's in the same units. These are PSIG. Remember that means pounds per square inch gauge. That means pounds per square inch above the atmospheric pressure. When you are going to do your calculations, you have to add 14.69 psi to the number that you are reading in order to obtain the actual pressure of the steam, and therefore to check whether this temperature of the steam in is consistent. The temperature of the steam out might be considerably lower for two reasons. First, the condensate might have already cooled down a little bit because it accumulates a little bit here in the bottom. Second, when the thermocouple is located in a pipe that's kind of popping out, so it gets cooled down by the environment. So be careful with this reading. Don't necessarily take it as an absolute correct value. The other information that is recorded in this panel is the time that it takes to fill the condensate collector. When you push the start button, the solenoid valve at the bottom of the collector is closed, and therefore the steam that has condensed and that escapes through as condensate through the steam trap starts to accumulate in that collector, and the computer is going to measure the time here that it takes to accumulate a fixed volume. As soon as the water reaches a level, that water will move a little automatic switch, and the computer can detect that the switch has been opened or closed through a 5-volt interface. So when you push the button, you provide a 5-volt signal to the computer that tells it start filling, and now I'm filling. Once the switch is pushed by the water, it turns it off, and then that 5-volt signal goes to 0 volts again, and the computer shows you the time elapsed. And because the volume is fixed, you can divide that volume by the time, and you get the flow rate of the steam that we have been used. The voltage is here, so at any time you will see what's the position of the switch. And also when you do that, you will be saving data. So during the time of collection of steam, all the data that are displayed here will be saved in a text file, so you can eventually also check that file in case you have doubts as to what was the correct temperature. However, since this is a steady-state experiment, it's enough that you record all the temperatures every time you're working. Now, this panel does not record flow rates. Therefore, you have to make sure that for every experiment you have recorded the flow rates from the rotameters for the feed supply, which is the circulating water, and for the cooling water. After you are done with it, you just push the quit and the program will stop. We have been talking about the overall heat transfer coefficient, and what we are going to review now is what you learned in heat transfer about convective transfer coefficients and how the overall heat transfer coefficient is the result of two different heat transfer coefficients. What we have is a surface, in this case the surface of a pipe made of copper, And we have two fluids. One is in the inside of that pipe, and one is in the outside. In the first pipe, the outside fluid is condensing steam, so it's hot. And the inside fluid is water, circulating water that's been heated. In the last four pipes of the heat exchanger, we have that hot water being cooled down. That's the inside fluid. And in the outside pipe, we have cooling water, just water coming from the tap. So those are two separate types of fluids. We're gonna discuss first the second half, the cooling half of the heat exchanger, where we have two liquids, a liquid inside and a liquid outside. So we're gonna have at this surface here a heat transfer coefficient H in the outside and a heat transfer coefficient HI in the inside, and a thin wall of metal. Now in this case it's a thin copper pipe which has high thermal conductivity, so we are going to disregard any thermal resistance that that pipe could be offering for the heat transfer between fluids. And in our case, because we are cooling, the heat is going to be moved from the inside to the outside. So this is the direction of the heat transfer, which means that there is a higher temperature here of the inside fluid. Then the heat is traveling to the wall, and there's an internal temperature at the wall. Then there is another external temperature at the wall, and then the heat has to travel to the temperature in the outside of the fluid of the pipe, the bulk of the fluid. So this happens at any specific point of the pipes. A moment ago you saw a drawing where we had these four pipes represented as a kind of labyrinth. Here the fluid is coming in hot from the preheater with the steam, and each one of these sections is being cooled separately, which means the temperature of the fluid that is circulating is decreasing as it's traveling. And therefore, this internal temperature and this external temperature, which is the temperature of the fluid going outside, are different at every single point of that pipe, but they stay constant all the time of the experiment for a fixed set of flow rates. That's why we call this steady state, because although the temperature inside here is changing with the position in the pipe, it is not changing in time. So the specific temperature that you have at a given point determines part of the properties of the fluids. For example, the viscosity is very sensitive to temperature. So the viscosity of the water, cooling water coming in here, is going to be somewhat different from the viscosity of the cooling water going out there. And the viscosity of the circulating water coming in here is going to be somewhat different from the viscosity of the circulating water coming out of the four lengths of pipe. That means the properties, the physical properties of that water are going to be changing during that trip. And you remember from your heat transfer that the heat transfer coefficient depends on three types of characteristics. The characteristics of the fluids. Specifically, the characteristics are the thermal conductivity, the density, the viscosity, and there are another set of properties that are the properties of the materials, in this case the copper or the pipe or whatever, and the geometry, the diameter of the pipes. For example, this pipe, this internal pipe here, has an internal diameter that corresponds to a nominal copper pipe of 1 inch, and that is 0.025 meters, or 2.5 centimeters, close to an inch. The outside pipe, which would be somewhere here, has a larger value, 0.056, and these are characteristics of the geometry. They also have a certain length, somewhat above 2 meters. That's part of the geometrical characteristics. So, number one, characteristics of the fluids. Number two, characteristics, geometrical and materials characteristics of the heat exchanger. Number three, operational regime. Do we have large flow rates, small flow rates? All those can be changed without changing the previous ones. So we have those three types of characteristics that we need to use to predict the behavior. Since the lab wants to predict a behavior and compare it to a measured experimental behavior, what we need is to remind you of these predictive tools that you learn in your heat transfer class. So how do we connect those three types of properties that we mentioned, that are the properties of the fluids, the properties of the geometry or materials made, and the other set of properties, which are the operational properties, such as flow rate, etc. Well, around 100 years ago, all this was figured out and put together in a series of non-dimensional equations. And to do that, we're going to use two non-dimensional numbers. There's the properties of the fluids are summarized in the Prandtl number, which is the ratio between the three characteristic properties of the fluid: the specific heat, the thermal conductivity, and the viscosity. These are three characteristic properties of the fluid. The Reynolds number also includes some of the characteristics of the fluid, because it's a function of the viscosity and the density, but it's also a function of the geometry of the system, because it contains a term for the diameter, and is also a function of the operational conditions, because it contains the average velocity. So what we are going to do is determine the Prandtl number, which is only a property of the fluid, of the material. It's not a property of the pipe or the system or whatever. But it depends on, this depends on they are a function of the temperature. Okay, so we're going to have to determine the average temperature. Here, these are a function of the temperature. This is not a function of anything, it's just fixed. Well, unless you consider the expansion, but it's so small. The velocity is a very weak function of the temperature, simply because the density can change and we use a volumetric measurement. So it's probably independent also. So these ones depend on temperature, this depends on the geometry of the system, and this depends on the velocity. The velocity, however, will have an indirect effect, in the sense that if you change the flow rate, you're going to change the temperatures, because the the heat transfer changes and the mass balances change. So changing the velocity will have an effect of temperature, which in turn will affect these other variables. I'm going to give an example using the assumption of turbulent flow. As you know, the Reynolds number provides a criterion to determine the type of flow. So if you have a Reynolds number that is below 2100, you are in the laminar regime. If you have a Reynolds number that is above 10,000, you are in the fully developed turbulent flow. And in between, you have the transitional flow. So by calculating the Reynolds number, you're also going to determine the type of correlations that need to be used. In the case of turbulent flow, the correlations that we are going to use are these. The Nusselt number is going to be equal to 0.023 multiplied by the Reynolds number to the power of 0.8 multiplied by the Prandtl number to the power of 1/3. Please note that I am neglecting the term, the correction term, due to the ratio of viscosities between the bulk and the flow. When you go to look, and the wall, sorry. When you go to look at the textbook, you will have a term here, but in our case, it's not very big, so we're going to neglect it. It's never a number very different from 1. Okay, so why is this very useful? Because the Nusselt number is directly proportional to the heat transfer coefficient. Nusselt is equal to the heat transfer coefficient multiplied by the diameter divided by the thermal conductivity of the fluid, not of the metal. So that means that because we can know this, or at least the average value, and we know the diameter, which is fixed, we can calculate the heat transfer coefficient for each one of the operating conditions that we have. So you guys are going to calculate your velocities, your density, viscosity, thermal conductivity, and specific heat at each average temperature, and with that you can calculate your value of H. And what you are asked to plot is the Reynolds number in a logarithmic scale against your heat transfer coefficient, which you can also calculate it on a logarithmic scale if you want. And you are going to get a line that has almost a slope of 0.8. It's not exactly 0.8 because the Prandtl number is going to change, not because the Prandtl number depends directly on the velocity at any time, but because changing the velocity changes the temperatures, and therefore changes the specific heat, thermal conductivity, and viscosity, and therefore you end up having a slight deviation from this. But this is you're gonna plot this as a line, not as a series of points, because this is a theoretical equation. And you could do this either for the internal or the external or the internal heat transfer coefficient. Right? So you're going to get sort of two theoretical lines that would look like that. Now, how do we go from the heat transfer coefficients to the overall heat transfer coefficient? That is the one that we can measure. We don't have any way to measure these guys. What we can measure is the overall experimental transfer coefficient. So let's see, how do we compute that? The overall heat transfer coefficient in the inside, and this is just because there's a tiny difference in the area inside of the tube and outside, is going to be equal to 1 over H0 multiply by dI over dO plus 1 over HI. Oh, sorry, this is 1 over UI. So this expression allows us to connect this value, which we are going to determine here. You could call this EI theoretical, and then there's going to be a UI, I'm sure that's invisible in the video, sorry. UI theoretical versus UI experimental. Okay? And what you want to observe is how close they are. So what you are going to end up doing is creating a plot of the Reynolds number in the inside, for example, and the UI here, and then you are going to have, let's say, some experimental values, which experimental values you're always going to plot them as symbols. And then you're going to plot, imagine, a theoretical curve, which you are going to plot as a line. So in your legend here, you should have that this corresponds to the value determined experimentally, and that line to the value determined theoretically. And then you're going to have to discuss why are they similar or different.
When finding the overall heat transfer coefficient experimentally, you're going to have to use a variety of temperatures collected throughout the entire apparatus. You'll know how much energy went into the system from the steam. You'll know how much energy was resulted in the change of temperature to the actual circulating water, and you'll know that the changes of temperature within the cooling water itself. All of these will go together in order to allow you to do an overall heat and energy balance across the entire system. This will give you your experimental overall heat transfer coefficient. Now, depending upon the exact flow rates that you use, your Reynolds number within the tubes will change. Also, the Reynolds number for your circulating water will be different from that of your cooling water. This is very important because we want to see the effect of overall heat transfer coefficient on the Reynolds number that you got for both the cooling water, the cooling section, the heating section, and for the cooling water itself. How do all of these different flow regimes play into the overall thermal characteristics of the system? What you may find is that as the Reynolds number changes, you may get experimental results that may have a bit of variation in them. This is normal. What we're looking for is trends in the overall system. You may begin to see outliers. If there is a phase change within part of the system, one of these may not make sense immediately to you. We want you to look at some of the data and analyze what could be occurring within the system at each one of these stages. When you're plotting experimental data, please apply single points to each data that you achieve. When applying theoretical calculations to a chart such as this, that is when you'd use a trend line. As such, do not give us data that is connected by lines unless you have a model that's actually resulting that you believe actually describes this data. Single data points tell a far better story than improperly used trend lines. If you have the option to repeat data, it's such that you can get a standard deviation for a single point of a Reynolds number, please give us an error bar showing your standard deviation. This will result in an overall better display of what you're actually able to find and achieve during the experiment.